Okay, so we're going to start with a brief review of Mosfets. We're going to talk about what they are, how they're made, how they work, and we'll talk a little bit about the transconductance curve as well. And then we'll go on and talk about a couple of applications for Mosfets tonight. So we'll talk about how we could use them for motor control. We can use them as switches to turn the motors fully on and fully off. And we can also use them for analog control, halfway on, 3/4 of the way on, and anything in between. And then we'll talk about using Mosfets as Cmos devices. So Cmos stands for complementary metal oxide semiconductor. This is a way to use a pair of Mosfets to achieve full control over a signal at a given point. Okay? For the lab tonight, we're actually going to build a motor controller, several different kinds of motor controllers using Mosfets, and then we'll do a demonstration of a Cmos device at the end as well. So, any questions about that before we get started? Okay, cool. So then let's start with a quick review of Mosfets. Okay? So, we said that MOSFET stands for metal oxide silicon field effect transistor. Thank you. It took me a minute. So, this was a special type of transistor. We already talked about bipolar junction transistors. So, this is another type of transistor. There were several different types of MOSFETs. One of them was drawn like this. This is the gate. Drain and the source. So, do you guys remember if this was an N-type or a P-type MOSFET?
N-type.
N-type, exactly. So it was kind of like a PNP BJT, right? And then there was the other type of MOSFET, the P-type, and that was drawn like this. It looked very similar, except that the arrow was pointing outwards. So again, this is the gate, the drain, and the source. And the arrow is pointing outwards. So the arrow is always on the source. With the N-type, the arrow is pointing inwards. With the P-type, the arrow is pointing outwards. Okay? So those were the symbols for MOSFETs. Now, we said that MOSFETs were a special type of transistor. When we looked at BJTs, we said that they were a transistor where current controlled current, right? A small amount of current flowing into the base of a BJT allowed a large amount of current to flow from the collector to the emitter, right? MOSFETs worked a little bit differently. With MOSFETs, we used a voltage to control the current. So the voltage on the gate determined how much current could flow from the drain to the source. So with N-type MOSFETs, the current flows from the drain to the source. With P-type, it actually flows from the source to the drain. Okay. So, but in any case, the voltage on the gate controls how much current is allowed to flow. So, since you have voltage controlling current, this is called a transconductance device. Trans meaning different things. So voltage controlling current. So MOSFETs are transconductance devices. And there was a transconductance curve that showed how the voltage affected the current. So if we looked at the current here versus the voltage, and we plotted this out, this was the transconductance curve. Now, when I drew this on the board last time, I didn't do it quite correctly. So let me point out a few things here. So first of all, there is a region where you can have voltage applied to the base. I'm sorry, to the gate, right? This is the voltage between the gate and the source. So there's a region where you can apply voltage to the gate, but not have any current flowing, okay? And then at some point, the current will start to flow. And this voltage where the current starts to flow is called the threshold voltage. It's sometimes abbreviated VTH. So in your lab last time, you guys were able to measure the threshold voltage. And there was also specifications in the data sheet which told you what that threshold voltage was. So it was supposed to be somewhere between 2 and 4 volts according to the data sheet, right? Do you guys remember what voltage you measured for the threshold voltage? 3 point something usually, right? Or 2.9 something, somewhere in that range. Usually pretty close to 3 if I recall. It might vary a little bit from device to device, but it was somewhere between 2 and 4 volts. And then, after the device starts to conduct current, what you see is that the curve looks something like this. So it's not a straight line, it's actually a parabolic curve. Okay? So, the more voltage you apply, as the voltage goes up, the current increases like the square of the voltage. Okay? So it's a parabola. The current goes like the square of the voltage. And then depending on the circuit that you've set up, you'll probably reach some maximum, and then the current will no longer increase after that. Okay? So that's the transconductance curve. So any questions about MOSFETs? Oh, yeah.
So there was at some point it was just maxed out where no matter how much more voltage you pour in, there's just no more current flowing, right?
Right. So that was determined by the type of circuit that you set up. So, like for instance, last time we set up a circuit that had a voltage source up here, and then had a resistor down here and ground. So if this resistor was 1 kilo ohm and this was 15 volts, even if this MOSFET acted exactly like a straight wire, you're never going to get more than 15 milliamps through this circuit, right? Because you would have 15 volts wired directly to a 1 kilo ohm resistor, and the maximum amount of current that would flow through there is 15 milliamps. So the MOSFET only can impede the flow of current. It cannot add more current to the system. Okay, so other questions about MOSFETs? Okay, cool. So today, we're going to use MOSFETs to do a couple of things. We're going to use them to control motors, and we're going to talk about how we can use a pair of MOSFETs as a CMOS device. All right? So let's start off by talking about motor control. Well, okay, I don't have to erase all that. Let's say that we've got our power source up here, and we've got our MOSFET. But now, instead of a resistor down here, let's say we hook up a motor. Okay. We know that an N-channel or an N-type MOSFET turns on when you have a high gate voltage relative to the source. So what we could do is we could have a wire over here and a switch. So if we close this switch, that's going to put a high voltage on the gate. Maybe we could have a pull-down resistor here going to ground, so that when the switch is open, the gate voltage gets pulled low. So this gate would either be getting a very high voltage or a very low voltage. So when it's very high, this MOSFET would act pretty much like a wire. So that would allow current to flow through there, and it would turn the motor on, right? So you could turn the motor completely on when the switch is closed. When the switch is open, the gate voltage would get pulled down very low, and it would be off. And so the MOSFET would not allow any current to flow, and the motor would stop turning. So we can use the MOSFET as a device to turn motors on and off. And we could do this with a switch like we've shown here, or we could also do it with, if we just hook the gate straight to a little microcontroller, and that microcontroller put out high or low voltage pulses, right? So we can turn the MOSFET completely on or completely off. So that's a good way to control a motor. And since we're using voltage to control the MOSFET, we can do this with the microcontroller, right? We could even have a very small microcontroller that can produce hardly any current, controlling a very large motor, because these MOSFETs can handle quite a bit of current. And the good thing about using the MOSFETs in the fully on or fully off configuration is that they're very efficient. And we can see that by looking at how much power they consume, right? We know Watt's law, so we can figure out how much power this MOSFET would be using when it's completely on and when it's completely off. So when it's totally on, it's acting pretty much like a straight wire. So there's no voltage between the drain and the source. So the power equation is Watt's law. It's current times voltage. So if there is no voltage, the power is going to be current times 0, so the power is going to be 0, right? So when this MOSFET is turned completely on, then it will have 0 or almost 0 power consumption, right? So that's good. If the MOSFET's not using any power, then all of the power is going to the motor where you want it to be. So this is good. Conversely, when the MOSFET is turned completely off, there is no current flowing through the MOSFET, right? So our power equation becomes current times voltage, and current is 0, so it's 0 times voltage. So again, we're using 0 power when the MOSFET is totally off. So when we use the MOSFET like a switch this way, it consumes very little power, right? So this is a good thing. Any questions about that? Yeah.
What exactly does the pull-down resistor do?
Yeah, so that's a great question. So imagine that we didn't have a resistor here. Let's think about what would happen. So when the switch is closed, what's our voltage going to be at the gate? 15 volts, exactly, because the switch is closed and it's connected directly to our positive voltage up here. We can call this 15 volts. So the gate voltage would be this positive supply voltage. So that's what happens when the switch is closed. Everything is great. What happens when the switch is open? What's our gate voltage then?
0.
Well, why would it be 0? There's nothing connecting the gate to 0, right? So if the switch is open like this and there's no resistor, the gate voltage is what we call floating. Basically, it's not connected to anything. And so it can fluctuate. It can be affected by the electricity in the air. It can be affected by the last voltage that was there. You know, if somebody walks by and swishes their pants a little bit, that can create some static electricity that can change this. So it can go up and down depending on environmental factors. So we say it's floating around. Now imagine that this voltage is controlling the current going through a big motor. So when somebody walks by, the motor turns on. When somebody else walks by, the motor turns off. This is not a good place to be, right? So what we need is we need to have this resistor here, okay? So this is usually a high value resistor, like 10 kiloohms or something. So when the switch is closed, this voltage at the gate is still about 15 volts, right? Because the gate is connected directly to a 15 volt supply with a wire, so the gate gets 15 volts. Now, when the switch is open, any sort of lingering electrons, lingering charge that was on the gate drains down through the resistor to ground, and this gate voltage gets pulled down to 0 volts. So that's why we call this a pull-down resistor. So it sets the gate voltage to a known level, 0 volts, when the other switch is open. So then any stray static electricity that might end up on the gate immediately gets drained through this pull-down resistor to ground, and the gate voltage stays at 0 until the switch is closed again. So that's what a pull-down resistor is. We could have done this a different way. We could have had a switch here, and we could have put a resistor here, right? Then when the switch was closed, the gate would get pulled down to 0 volts. When the switch is open, the gate would get pulled up to 15 volts. So it would work that way too. And in that case, this is called a pull-up resistor. Okay? So if it's a resistor going between a pin and the positive voltage, it's called a pull-up resistor. If it goes between a pin and a ground, it's called a pull-down resistor. And MOSFETs really are very sensitive to this stuff. You can actually try this out for yourself tonight when we're controlling the motors. What you can do is you can leave the gate not attached to anything, and you can take your hands and grab one side, one hand onto ground and the other hand touch the gate, and it should make the motor stop. And then you can grab one hand on the positive voltage and touch the gate with the other hand, and it should make the motor go. And most likely the motor will keep going even after you move your hands away. So just the little tiny residual charge that was able to travel through your body and land on that gate is enough to keep the gate open and allow the motor to keep turning. So you should try that out when you build your circuit. Yeah.
On other Mosfets, we don't want to do that, but the ones that we have in the lab here, we should be okay.
Right, exactly. So this is all to do with small charges being transferred from the, either the positive voltage or the ground to the gate through your body. Normally, you would be wearing static discharge equipment if you were handling these types of MOSFETs, because MOSFETs are very sensitive to static electricity, like we discussed last time. And so normally you would be wearing the static discharge stuff, and that would remove any of that charge that might have landed on your body. But these are particularly bomb-proof MOSFETs, and so it's not as much of a concern here. Yeah. Other questions? Yeah.
I have a question about power equals 0 when the current is 0, right?
Right.
How can we see the diagram on exactly which part we should take off and then it comes to current is 0?
Okay, so what happens is that when the gate voltage is low, that's over in this part of the transconductance curve. So that's where no current is being conducted. So basically the MOSFET is acting like an open circuit, like there's no connection between the positive 15 volts and the motor in this case. So if there's no connection between the 15 volts and the motor, that would mean that there is no current flowing through there. It's basically a very, very, very high resistance. So no current, or almost no current, is allowed to flow. It's somewhere in the microamps, I think, is how much current is actually flowing. So it's essentially zero. Is that what you were asking? Okay. All right, so we've seen how we can use MOSFETs to turn motors on all the way or turn them off completely. But sometimes that's not good enough, right? Sometimes we want to be able to turn the motor on halfway. I mean, imagine if you were driving an electric car and you could either go pedal to the metal or full stop. Wouldn't be very fun to drive, right? Well, it might be exciting for a little while, but it's not enough control. Sometimes you need to be able to control motors more finely. So there's a couple of ways that we could do this. The first thing that comes to mind is that we could use this middle part of the curve. So we could apply maybe, if we wanted to get half the total voltage, we could apply, or half the total current, we could apply, this much voltage and get about half of the current that way, right? So we could apply not 0 volts or 15 volts, but somewhere in between, right? Maybe 4 volts or 5 volts, right? You saw that last time. You were able to vary the voltage, and that varied the current. So, so say this motor takes, a maximum of 1 amp. So you could vary the voltage on the gate until you were getting, you know, half an amp down here, right? So that would control the speed of the motor, but there's a problem with that. The problem is that if you do that, now you've got current flowing through your MOSFET, but you've also got the voltage across your MOSFET. Okay? So now your current and your voltage exist. So basically, the MOSFET is taking a bunch of the energy that should be going to the motor and converting it into heat. And this is bad for a couple of reasons. First of all, the energy is not going where you want it to go, right? It's being turned into heat, which is something that's useless to you. So if you were paying for this electricity, you'd be paying to heat up the air, which is not good. The second thing is that a lot of heat inside of electronics is usually a bad thing, right? If it gets too hot, it can start melting things. Even if it doesn't get too hot, you have to put big fins on there or something in order to dissipate that heat and move it away from the device. So you're wasting energy and you're turning it into heat, which then you have to cope with as well. So turning the gate on halfway is something that would work, but is very inefficient. Does that make sense? So what else could we do if we wanted to control our motor, but have our MOSFET still be pretty efficient? Any ideas? Well, we can do something called pulse width modulation, PWM. The way that this works is that you create pulses of voltage on the gate. So if you were doing this with a microcontroller, you would have your little microcontroller chip over here, and there would be the little pins, and you'd have one pin connected to the gate, and you would be creating pulses of voltage on this pin. And those pulses would either be 0 or 5 volts. So you'd be turning the MOSFET either completely off or completely on. But these pulses would be happening very, very quickly. Okay? So if you looked at them on a chart, what you would see is something like this. You'd see these pulses, and they'd be turning the voltage either all the way on or all the way off. So the MOSFET is either all the way on and allowing the current to flow, or it's all the way off and it's blocking. And remember, the MOSFET is very, very good, very efficient in both of these states, right? We saw that before. So you're switching back and forth between these very efficient states. And what this does is that you can vary the width of these pulses to vary the amount of time that the MOSFET is on. And by doing that, you change the average voltage. So if the MOSFET is on for half the time and off for half the time, then the average is about half. So you would get out about half of the maximum current that you could get from your circuit. Okay? if you wanted the motor to be on more, going faster, what you could do is you could make the on pulses longer and the off pulses shorter. Okay? So if it were on for 90% of the time, then you might get about 90% of the maximum current. If you wanted to have less current flowing through there, you could leave it off for more of the time. So you could have it off mostly and just have a short pulse being on. And if this were, say on for 20% of the time, then the MOSFET would be giving you, or maybe 20% of the maximum current that the device could handle, that the motor could take. Okay? So by varying the width of these pulses, you are able to vary the amount of current that's flowing to your motor or to whatever device you want to control. So you're switching back and forth between these very efficient states for the MOSFET. So you're still getting a high efficiency, and yet you're able to control the speed of the motor in an analog way. Okay? So you're using digital pulses to create an analog control of this motor. Yeah?
Would you actually be able to see those pulses on the source, like would your motor active, and would you?
Well, so it depends, right? It depends on the frequency of the pulses. So if you made these really slow, like on, off, then you'd be able to see the motor kind of speeding up and slowing down, speeding up and slowing down. But what happens is that in practice, these pulses are usually created at tens of thousands of hertz, or 20, in the tens of thousands of hertz. So that's way too fast for human sight, and the motor actually smooths out some of that that switching. Human hearing only goes up to 20 kilohertz. So oftentimes the pulses are created above 20 kilohertz, because if it's in the 10 to 20 kilohertz range, it can actually create a high-pitched buzzing noise or whining noise that can really be irritating. So often it's created at a range that's above human hearing. And then when it's that fast, the motor really smooths it out very well, and people absolutely cannot notice. So, yeah?
Does the MOSFET take any time to switch back and forth itself?
It does. It does. So I'm drawing these lines vertical, or as vertical as I can do on the whiteboard, and that would be an instantaneous change. But to your question, there is actually some small but finite amount of time that it takes to go from negative to, or from off to on, and from on to off. And during that time, the MOSFET is in the less efficient region. So you don't want the frequency to be so high that those transitions are happening too often, because that can lessen the efficiency of your device. Certain MOSFETs are designed specifically to have very quick changes, so that they are able to be as efficient as possible for these types of applications. Other questions? Okay, so that's how we can use digital pulses to create an analog control of a motor, or of other things too. You could imagine that this could be a light, right? Overhead lights, you can make the lights brighter or dimmer, depending on the width and the duty cycle of these pulses. So I should define that term. The duty cycle is how much of the time the pulses are positive. So if the pulses are positive for half the time and off low for half the time, then that's a 50% duty cycle. If they're on for 90% of the time, that's a 90% duty cycle. So duty cycle is just the amount of time that the pulses are on, or the percentage of the time that the pulses are on. Okay. All right. So that's a little bit about analog control. So the MOSFET here, if you just have one MOSFET connected to a motor or to any other device, this MOSFET in this configuration could set the voltage here to be high, right? If we turn this MOSFET on and allow the current to flow, essentially we're creating a wire from the 15 volts down to this position. So we could set this voltage to be high, right? But if we turn the MOSFET off, then essentially we have created an open circuit here. So this is sort of like the situation that we talked about a minute ago. You've got a wire that's not connected to anything, right? So that wire would have a floating voltage when the MOSFET is not turned on. So a single MOSFET could set the voltage to be high, or it could set the voltage to be floating. We could use a P-type MOSFET, and then that P-type MOSFET could set this voltage to be low if the P-type was connected to ground or a negative source. We could set this voltage to be low. But again, when the P-type was turned off, the voltage would be floating. So if you just have one MOSFET by itself, your voltage is going to be floating in some situations. And with large electronics, that's not so much of a problem, right? You know from experience that the static electricity from your hand is not going to make a big motor run wild, right? So it's not such a big deal, but sometimes it's still not ideal. Sometimes you would still like to be able to set the voltage high or low. For instance, if you wanted to be able to control the direction of flow of this, or of rotation of this motor, it would be nice to be able to set this voltage to be high or low. And to do that, we need two MOSFETs that work together with each other. That's what Cmos is. Okay? Cmos stands for complementary metal oxide semiconductor. So a CMOS device is a device that uses two MOSFETs together. So it would be something like this. this is a P channel, and this is an N channel MOSFET. And then this is our input over here. And our output comes right there. So what happens is that when the switch is in this configuration, the voltage at the gate of the N-channel MOSFET is high. And when you have a high voltage at the N-channel gate, that allows current to flow through the N-channel MOSFET. And so that pulls this output voltage low, right? So the switch in this configuration makes the output voltage low. This also puts a high voltage at the gate of the P-channel MOSFET. And a high voltage at the gate of the P-channel MOSFET means that this acts like an open circuit. So you've got this open circuit up there, and you've got basically a wire down here. So the voltage at the output goes low. If you put the switch in the other configuration, like this, now you've got a low voltage here. So a low voltage on the gate of an N-channel MOSFET means that it's open, so it's like it's not even there. A low voltage on the gate of the P-channel means that it's acting like a wire. So you've got a straight wire from your source voltage to the output. So the output voltage goes high. So in one configuration of the switch, the output voltage is low. In the other configuration, the output voltage is high. So these two MOSFETs work together to always set the output voltage. There's no condition where the output voltage is floating. Okay? So that's called a MOSFET, or a CMOS device. And there are many applications where CMOS devices are actually used. You guys may have heard of CMOS digital cameras. The sensors on those cameras use CMOS technology to detect light. Also, memory for computers, as well as microprocessors, use CMOS technology. So this is used all over the place. When you're talking about memory, everybody's talking about highs and lows, zeros and ones, right? Well, what is really going on is that there's millions and billions of these little CMOS circuits in there, and they're all storing either high voltage or low voltage. So the output is either high or low. So these are the actual ones and zeros inside of computer memory. This is how your programs are stored, your photos, your videos, everything that's stored in memory is stored in little tiny rows and rows and rows of CMOS devices. So, any questions about that? Okay. Cool. So we've talked a little bit about motor control. We've talked a little about CMOS devices. So let's talk a little bit about our lab then. The first thing that you're going to do in lab is you're going to build a circuit that's pretty much like this. the gate and the motor positions are reversed, but the idea is very much the same. There's a switch there like that. And you're going to use a MOSFET to turn a motor on and off. We've actually got little motors here, so every group is going to grab a motor, and then you'll be able to turn them on and off using this, using the MOSFET. So one side of the switch is going to power, and the other side of the switch is going to ground. So really the switch is more like this. And we're not going to use actual switches here. What you're going to use instead is a little piece of wire. So you're going to have this little piece of wire, and you're either going to plug it into the power or the ground. Okay, so you're just going to move it back and forth like that. And what you'll probably notice is that when you plug it into the power, the motor turns on, and then when you unplug it from the power and it's floating, the motor is going to stay on, okay? Because there's nothing that has discharged that little amount of electricity that was still on the gate. When you plug it into the ground, the motor is going to stop. But then when you unplug it from the ground, the motor is still going to stay off because, again, you don't have anything to change that state. So when you'll see that sometimes when the switch is not plugged in, the motor's off, and sometimes it's on. And like I said, it's an interesting thing to try to just hold that wire with one hand and then touch either the power or the ground with the other hand. Often you can make the motor turn on and off just by the small, tiny amount of electricity that conducts through your body. Okay. So that's the first circuit that you're going to build. The next circuit is pretty much the same, except that in this case, you're not going to just use a little switch here. You're going to hook the gate up to a function generator. So you'll have a function generator, and you're going to use a square wave output. So the square wave should be going between 0 and 5 volts. When you do this, the easiest thing to do is to use the TTL output from your function generator. So this is the plug that's on the left-hand side of the function generator. So you're going to take your BNC cable and plug it into the left side of the function generator rather than the right where you normally plug it in. Okay? That'll set it to be automatically 0 to 5 volt output. And then what you're going to do is that you're going to find the knob on your function generator that says duty, and you're going to pull that out. That will allow you to vary the duty cycle of the TTL. So remember we talked about how you could have a short duty cycle or a long duty cycle, a low or high duty cycle. So you pull that knob out and then you can change it around. And that should allow you to make the motor speed up or slow down. Okay? The next thing is that you're going to build a circuit very much like the first one, except you're going to use a P-channel MOSFET instead of an N-channel MOSFET. Okay? And then finally, you're going to build a Cmos Logic circuit. So the Cmos Logic circuit, well, it's very much like this. On the output, you're going to have two LEDs. So you're going to have a green LED up here with the resistor, and then you're going to have a red LED down here. So when this output is high, the red LED should go on. When the output is low, the green LED should go on. So you should be able to flip this switch back and forth and change whether the red LED or the green LED is on. Okay, so you should be able to make, it should be one at a time though, it should not be both. And it should not be neither either. One of them should always be on and the other one should always be off. You can flip it back and forth. So, any questions about that? All right, cool. Then let me take roll, and you can have a break and start the lab.